Welcome back to the deep dive. It is Wednesday, February 18th, 2026. And I have to be honest with you right out of the gate. If you are a tech watcher, if you are someone who obsesses over the silicon that powers our daily lives, the last few weeks have been absolutely relentless.
Well, relentless is the word for it.
I mean, I looked at my RSS feed this morning and I just wanted to close my laptop and go live in a cabin.
It really has been intense. It's the classic drinking from the fire hose scenario, but I
Yeah.
think the fire hose has been upgraded to, I don't know, waterfall.
Waterfall, yeah.
We are fresh off what the industry is kind of jokingly calling the AI Spring Festival Gala.
I love that name, by the way. It sounds so festive, but I imagine for a systems engineer or a developer, it sounds more like a massive pile of homework that just got dropped on your desk.
It absolutely fits, doesn't it? Because it's been this just explosion of activity,
Yeah.
and specifically coming out of the Chinese tech sector. You have DeepSeek, you have Alibaba, you have 01.AI,
Right.
and they aren't just releasing these dense white papers that nobody can actually use. They're dropping weights, they're dropping code, architecture diagrams. It is a period of intense, almost chaotic innovation.
And amidst all that noise, it is so easy to miss the signal. You sent me a stack of papers yesterday, and honestly, I was drowning in them until you pointed to this one specific project. You said, ignore the noise, look at this.
Right. Because I think amidst all the hype, we are looking at a structural paradigm shift. And I know, I hate using that phrase.
You usually forbid us from using it. I was going to say, that's a forbidden phrase on the show.
I know, I do. It's so overused, it usually just means we change the font size. But in this case, we are talking about a fundamental change in how we run artificial intelligence on local, consumer-grade hardware.
Okay, so this isn't just a software patch or a slight percentage point increase in token speed.
No, not at all. We are talking about changing the physics of how these models think and, maybe more importantly, how they remember.
And to make this concrete, because we love a good case study here to ground all the abstract math, we're going to look at this through the lens of a specific project. It's called Kayacord.
Kayacord, yeah. It's a fascinating testbed, a perfect example for what we're talking about.
So for you listening, let's just set the scene. Imagine an autonomous support bot. But this isn't the annoying chatbot on your banking website that just, loops you in circles.
No, not at all.
This is running on a Discord server, and it's a server dedicated to technical support for Arch Linux and KDE Plasma.
Which, if you know anything about the Linux ecosystem, is not a place for lightweight questions.
Not at all.
You don't go there to ask how to change your wallpaper. You go there when your kernel keeps panicking or your display server is crashing and you're staring at a command line. That is a heavy-duty technical environment.
Exactly. The users there are ruthless if you give them bad info. But here is the constraint, and this is really the key to our whole deep dive today. This bot isn't running on a massive server farm in a data center somewhere in the Nevada desert.
Right. This isn't some cloud-based behemoth.
It's running on an edge device, specifically a desktop PC. And the hardware is an NVIDIA RTX 3060 with 12 gigabytes of VRAM and an AMD Ryzen 5 9600X.
That is the everyman rig of 2026.
Yeah.
Really, it's a solid setup. If you're a gamer, it's a great machine. But in the world of large language models, 12 gigs of VRAM is, let's just say it's tight.
Tight is a good word.
It is a very, very strict budget. You have to be incredibly efficient.
So the mission today, what we're going to explore is the migration this project is undertaking. They are moving from an established architecture, which is Google's Llama 3.
Which is a great model, to be clear.
A very good model. But they're moving to the newly released Alibaba Qwen 3.5 ecosystem.
And I want to be really clear here. This isn't just swapping Coke for Pepsi. This is the core conflict of our discussion today. It is a battle between dense models like Llama 3 and these new hybrid models represented by Qwen 3.5.
And I have to bring up the skeptical engineer perspective here, too. I'm going to try and play that role today.
Please do.
Is this just hype? Is it just new, shiny toy syndrome? Or is it actually a leap forward in utility? Does it actually let you do something you couldn't do before?
That is absolutely the right question to ask. And by the end of this deep dive, I want us to understand how a change in the underlying mathematics allows a gaming hardware that is 5 years old at this point, to do what used to require enterprise clusters.
Okay, let's do it. Let's unpack this. We need to start under the hood. We have to talk about this engine swap. So dense versus hybrid.
Right. So the status quo for a while now has been the dense transformer. That's Llama 3. It's really been the gold standard for small, efficient models for the last couple of years.
Okay, hold on. Dense. When I hear dense, I think of like a really heavy fruitcake. What does dense mean in terms of silicon and neural networks?
That's actually not a bad way to visualize it. I like that. Imagine a committee meeting in a huge boardroom. In a dense model like Gemma 3 or the older GPT models, every single time a question is asked, every single person in that committee room has to look at it, think about it, and vote on the answer.
Wait, even if the question is incredibly simple, like what is 2 plus 2?
Exactly. You have the professor of astrophysics, the poet laureate, the master chef, and the janitor, all stopping what they are doing to calculate 2 plus 2. Every parameter is active for every single calculation.
That sounds incredibly inefficient. Why would anyone build it that way in the first place?
Well, it's thorough. That's why these models are so smart. They bring their whole brain, their entire collective knowledge, to bear on every problem. But the cost is what we call the quadratic complexity problem.
Ah,
It's
yeah.
often written as O of n squared.
I remember seeing that in computer science classes and just sweating, but let's refresh the intuition for everyone. Why is quadratic complexity the villain in this story?
Okay, so think of it like reading a book. In a linear world, a normal world, reading page 100 takes the same amount of effort as reading page 1. You just turn the page, you read the words, simple.
Right.
But in a quadratic world, like these dense transformers, as the conversation gets longer, as the context grows, the computational cost explodes. It's like reading a book where every time you turn a page, the book itself physically gets heavier.
Oh, I like that analogy. So by the time I'm at page 50, I'm struggling to hold it up.
By page 50, your arms are shaking. By page 100, you literally cannot lift the book to read the words. It's crushing you.
And in AI terms, this leads to something you mentioned called context rot, right?
Exactly. Context rot is a huge problem. The model gets slower and slower, and weirdly, it gets dumber as the chat history fills up.
How can it get dumber?
It starts forgetting the beginning of the conversation. It's like
Yeah.
the weight of the book is so heavy it can't remember what was on page 1.
Right.
The sheer computational weight of processing the entire history becomes too much for the hardware.
Which is a complete nightmare for a support bot, right? I mean, think about a debugging session. You're pasting in error logs, you're chatting back and forth, you're trying different commands. That book gets heavy really, really fast.
Precisely. And suddenly, the bot forgets what version of Linux you're running, or it starts hallucinating because it's, for lack of a better word, exhausted.
Okay, so enter the challenger Qwen 3.5. This is the hybrid.
The hybrid. And it combines two very distinct technologies to solve this heavy book problem. First is something called gated delta networks, or GDN, and second is sparse mixture of experts, or MOE.
All right, let's take those one by one because they sound like Star Trek technobabble.
They do.
Gated delta networks. This is the linear attention piece,
Yes,
right?
this is the magic trick.
Yeah.
This is where the physics changes. Qwen 3.5 alternates its layers in the neural network. For every 4 layers, 3 of them use this gated delta network, which is a form of linear attention. It's very computationally cheap.
And the fourth one.
Only 1 layer out of the 4 uses the standard heavy quadratic attention.
So it's like 3 light layers, 1 heavy layer. 3 light, 1 heavy, all the way up the stack.
You got it. That's the architecture. And the result of that ratio is that the overall scaling becomes linear. It's O of n.
So going back to our book analogy, what does that look like now?
Instead of the book getting heavier, you're just scrolling a digital screen. The effort to scroll down to page 1000 is exactly the same as the effort it took to read page 1. There is no added weight.
That is a massive difference. I mean, fundamentally, that changes the entire user experience. You don't get that degradation over time.
It's huge. The benchmarks show a decoding throughput increase of anywhere from 8.6 times to 19 times when you're dealing with long contexts.
And long context is anything over, what, 32,000 tokens or so?
Yeah, around the 32K mark and beyond. That's where you really see the separation.
So for our bot, for Kayacord, that means the first token latency, that snappy responsive feeling when you hit enter, it stays fast even if the bot has been reading logs for an hour straight.
It absolutely does. It breaks the curse of the long context. But that's only half the story.
Okay.
The other half is the mixture of experts.
The MOE.
The MOE. This is about being sparse rather than dense. So we're moving away from the fruitcake model. Exactly. We're getting rid of the fruitcake. So let's look at the flagship model, just for scale. The biggest Qwen 3.5 model is listed as having 397 billion parameters.
397 billion. Okay, that sounds like you need a supercomputer. I mean, you'd need a warehouse full of GPUs to run that.
You would if it were dense, but it's sparse. And what that means is it only activates about 17 billion of those parameters for any given token it processes.
Wait, walk me through that again. It has a brain the size of nearly 400 billion, but for any given thought, for any single word, it only uses 17 billion.
Correct. Let's go back to our committee analogy. In the dense model, everyone votes on everything.
Right, the astrophysicist and the poet.
Exactly. In the mixture of experts model, it's more like a massive hospital. You walk into the emergency room with a broken arm. You don't need the cardiologist, the neurologist, the pediatrician, and the oncologist to all come stare at your arm.
No, of course not. That would be a ridiculous waste of everyone's time.
Right. You just meet a triage nurse and the orthopedic surgeon.
Okay, so who is the triage nurse in this Qwen model? What part of the network does that?
It's a tiny, very lightweight neural network that sits in front of the experts. It's called the router. And every time a token comes in, a word, a piece of code, whatever, the router looks at it and says, aha, this is a Linux kernel error. I need to send this to expert number 4 and expert number 42.
So if I'm asking it about Arch Linux kernel drivers, it's waking up the kernel driver experts, but it's letting the, I don't know, the French poetry experts sleep.
Exactly. And they stay completely asleep. They don't consume a single watt of compute power. They don't take up any VRAM. They are just dormant.
So you get the knowledge base of a giant 400 billion parameter model, but the running cost and the speed of a much smaller model.
That is the promise.
Yeah.
And a local application of this, the 9B variant that we'd run on our RTX 3060, it uses this exact same logic. It allows for what the paper calls frontier class reasoning, but in a package that fits into the VRAM of a consumer card.
That's the how. And logically, I get it. The math makes sense. You save memory, you save compute. But now we need to talk about the what. How does this thing actually perform?
Right.
Because if it's fast but stupid, nobody cares. If I ask it how to fix my Wi-Fi and it tells me to bake a cake really, really quickly, that's not helpful.
Fair point. A very fast idiot is still an idiot. Speed is nothing without accuracy. So let's look at the benchmarks. And remember, we are comparing this open weights model against the absolute heavy hitters of early 2026. We're talking GPT 5.2, Claude 4.5 Opus, Gemini 3 Pro.
And just to clarify for everyone listening, Qwen is open weights, right? Apache 2.0 license.
Yes, that's a huge point. You can download it, you can run it offline on your own machine, you can modify it. That gives it a massive strategic advantage for privacy and commercial use compared to proprietary APIs where you're sending all your data to OpenAI or Anthropic.
Okay, let's hit the scores. General Intelligence, MMLU Pro.
MMLU Pro, and this isn't the old MMLU you might remember from 2024. The Pro version is much, much nastier. It has 10 multiple choice options per question instead of 4.
Oh, wow.
So you can't just guess. It requires complex reasoning chains just to eliminate the wrong answers. On that test, Qwen 3.5 scores an 87.8.
That sounds really high, but context is everything. What's the competition doing on that same test?
It beats GPT 5.2, which scored 87.4.
Wait, pause for a second. A model architecture that can run on consumer hardware is outperforming the flagship proprietary GPT 5.2 on a general intelligence benchmark.
Well, to be precise, the flagship 397B parameter Qwen model does. But the architectural advantages, the reasoning capability, that trickles all the way down to the smaller models. The reasoning capability is inherent to the design.
Okay.
But for Qwen, general intelligence is actually less important than technical proficiency. We don't need a philosopher. We need a Linux admin.
Right. Can it code? Can it use the terminal? Because if I paste a bash script into the chat, I need it to understand what barm-r5 does and warn me.
The coding scores are stellar. It scored a 91.3 on AM 2026, which is a math competition benchmark, and a 76.4 on SWE Bench Verified. But the number that really jumped out at me, and this is the one that sold me on the Qwen migration, was a new one called Terminal Bench 2.0.
I haven't heard of that one. What does that measure specifically?
It measures the ability to actually use a command line, to interact with the shell. It tests if the model can navigate directories, grep for files, manage permissions, and execute scripts without crashing the system or, doing something catastrophic.
That sounds incredibly important for a support bot.
It's everything. The previous version, Qwen 3 Max Thinking, scored a 22.5 on this benchmark.
Ouch. That's not great. That's delete your home folder by accident territory.
It is. It's dangerously incompetent. Qwen 3.5 scores a 52.5.
That is a massive jump, more than double.
It's a completely different class of capability. It implies that the bot effectively understands shell commands, environment interactions, and flags. And for an Arch Linux support bot, that is the difference between it saying, I think you should try this command, maybe, and here's the exact syntax to fix your problem, and here's why it works.
It's the difference between a suggestion and a solution.
Precisely. And then there's the agentic side of things. We talk about agents all the time, but what does that really mean here? It means following complex instructions and using tools properly. On the IF bench, that's the instruction following benchmark, it scores 76.5. It absolutely crushes Claude 4.5, which is way down at 58.0.
Wow.
And on BrowseComp, which measures its ability to browse the web, it's at 78.6.
So it can navigate UIs, it can call tools, it can manage its own state without getting confused or lost.
Exactly. And this is interesting. The paper notes, it's less sycophantic. It's less likely to just agree with you if you're wrong. It's more likely to say, wait, user, that command you're about to run is going to wipe your drive. Don't do that.
Which is exactly what you want in a support bot. You want a partner, a sanity check, not just a yes man.
You got it.
Now, I want to pivot. Let's get down to the hardware reality, the nitty gritty, because we keep mentioning this RTX 3060. 12 gigabytes of VRAM. Why is the specific number, 12 gigs, such a battlefield for local AI?
It's the defining constraint. It's the line in the sand for so many users. If you have an RTX 3060, the box says 12 gigabytes, but you don't actually have 12 gigabytes available for your AI.
Right, because I still need to see my desktop. I have a monitor plugged in. I'm running an operating system.
Exactly. You're running Linux, probably KDE Plasma 6, if you fit the specific user profile. That desktop environment, the display server, the window compositor, that's what I call the system tax.
The system tax. I like that.
It takes about 1 to 2 gigabytes of your VRAM just to keep the lights on and make the windows wobbly.
So you're really working with 10 gigs, maybe 10.5 if you're lucky.
Roughly 10 gigabytes on a good day. Now let's look at Llama 3, the 12B parameter model, which is the comparable one. We have to talk about quantization here for a second.
That's the compression, right? Making the model file smaller.
Essentially, a raw, full precision model usually stores its brain, its weights, in 16-bit precision. That's high fidelity. But it's huge. To fit these models on consumer cards, we chop that precision down to 4 bits.
Okay, so that must have a cost. Does that make the model dumber?
Surprisingly, barely. The performance loss is minimal for most tasks. It's like lowering the resolution of a video from 4K to 1080p. You can still see exactly what's happening, but the file size drops by 75%.
So that 12 gigabyte card suddenly feels a lot bigger.
It does. But even with that compression, the 4-bit Llama 3 12B model takes about 8 gigabytes of VRAM just to store the weights of the model, just to load the brain into memory.
Okay, doing the math. 10 gigs available minus 8 gigs for the brain. You have 2 gigs left over.
2 gigabytes left for everything else. Primarily, that's the KV cache.
Which is the short-term memory.
That's the short-term memory. That's the context window. That's the conversation history.
2 gigs sounds like a decent amount of text, though.
It sounds like it, but in the high-dimensional space of Transformer model, it fills up instantly. 2 gigabytes gets you maybe 16,000, 24,000 tokens of context.
That sounds like a lot, but in a technical debug session with logs and configs.
It goes so fast. You paste one long system log file, have a little back and forth about it, maybe paste a config file, and boom, you hit the wall. Your VRAM is full, and when you hit that wall, you trigger the 200-second bug.
I love that name, the 200-second bug. It sounds like a horror movie title for a sysadmin. What is actually happening there under the hood?
It is a horror movie for the user. When the dedicated high-speed VRAM fills up, the system has no choice. It has to start swapping that context data to the regular system RAM, the CPU RAM.
Which is much, much slower. It's not designed for that kind of parallel workload.
Orders of magnitude slower. Your generation speed drops from a comfortable 40-plus tokens per second, which feels like natural speech, to maybe 3 to 6 tokens per second.
Oh, that's painful.
It's agonizing. It's called context thrashing. The bot basically freezes. You type a message, hit enter, and you are literally waiting 3 minutes for a reply.
It just completely breaks the illusion of intelligence. It makes you feel like the computer is broken.
It does. So how does Qwen 3.5 change this VRAM math?
Yeah, run the numbers for the new engine. What does it look like?
Okay, so the comparable Qwen 3.5 is a 9B model in this variant. At the same 4-bit quantization, the weights only take up about 5.5 to 6 gigabytes.
Okay, so 10 gigs available minus, let's say, 6. We have 4 gigs left over.
4 gigabytes, maybe even 4.5. We've doubled, maybe even tripled the headroom for context.
So the practical context window goes from, what, 16K on a good day?
To easily 64,000 tokens or more. You can fit an entire debugging session, the error logs, the relevant documentation, and the user's panicked rants all into the fast GPU memory without ever touching the slow system RAM.
So the 200-second bug just It just evaporates. It ceases to be a problem.
It's gone. It's solved at an architectural level. That is the difference between a toy and a tool.
It really is. It allows the bot to ingest a massive error log without crashing or slowing to a crawl. It changes the behavior from sort of reactive and forgetful to comprehensive.
Exactly.
But it's not just about text anymore, is it? We need to talk about the eyes of the agent, multimodality.
Yes, this is another area where the architecture shifts dramatically and I think in a very important way. Gemma 3 uses what we call frozen adapters.
Explain that. Frozen adapter sounds like a plumbing part you'd find at the hardware store.
It kind of is,
Mm-hmm.
in a way. Imagine Gemma 3 is a blind genius. It's brilliant with text, but it can't see. To understand an image, it uses a separate, bolted-on tool, a vision encoder called SIGLIP, that looks at the image and then describes it to the main brain in words.
So it's a translation. It's not direct perception.
Exactly. The vision part is frozen. It wasn't trained alongside the language brain. It's an attachment. It's like someone describing a photograph to you over the phone.
Okay, I see a computer menu. It has some text on it. Some icons are blue.
Precisely. You get the gist, but you miss the nuance. You miss the tiny details, the pixel-level information. Qwen 3.5 uses native multimodality. It's what's called an early fusion model.
Meaning?
It means it was trained on text, images, UI screenshots, and even video clips all at the same time from the very beginning of its training. There is no separate adapter. The model looks at the image directly with its own eyes.
So it's not hearing a description, it's seeing the pixels. It understands the spatial relationship between elements on the screen.
It is seeing the pixels. It processes images up to a resolution of 1344 by 1344. It can even analyze 60-second video clips at 8 frames per second.
Okay, so what does that mean for Kayacourt? Give me the user story. How does this help?
Think about a super common technical support scenario. A user posts a screenshot. They say, hey, my KDE Plasma menu looks weird. The font is all garbled.
The classic Linux problem. I've been there.
We've all been there. Gemma might get a text description from its adapter. A computer menu with some text. It doesn't know what is wrong. Qwen sees the specific pixel alignment. It recognizes the font rendering artifact. It sees the specific icon set being used.
So it can be much more precise.
It can say, oh, I see the problem. You have sub-pixel rendering turned off in your compositor settings, but your font configuration expects it to be on. Here is the exact shell command to fix it.
Because it has seen that specific visual glitch thousands of times in its training data?
Exactly. And the benchmark that proves this is called OmniDocBench. It measures understanding of complex documents and screenshots. Qwen 3.5 scores a 90.8. That surpasses many of the big proprietary models. It is incredibly good at reading screens and documents.
So we have a brain that scales linearly. We have eyes that see natively. But what about long-term memory? This brings us to the URAG upgrade.
Right, retrieval augmented generation. This is how the bot knows things it wasn't explicitly trained on, like the latest ArchWiki updates that came out this morning.
And the old way with the Gemma 3 setup was using an embedding model called Nomic Embed Text.
Which is a solid embedding model, don't get me wrong. Nomic is great, but it had a fundamental limit.
Yep.
8,192 tokens.
So you had to take your documents, your knowledge base, and chop them up into small pieces.
Exactly. You're chopping up a technical manual into paragraphs, and sometimes the context gets lost at the seams. You retrieve a paragraph that says, set this value to true, but you've lost the paragraph before it that explains what this value is.
It's like reading a book with half the pages torn out. So Qwen is releasing a companion model for this, Qwen 3 embedding 4B. What are the stats on that?
The context length is 32,768 tokens.
Wow. Okay, that's a fourfold jump. That's a novella.
It means you can embed an entire code file as a single memory. You can embed a whole chapter of documentation as a single coherent chunk. You don't have to chop it up into these tiny confusing fragments anymore. The bot can retrieve the whole concept, not just a snippet.
And there's this concept mentioned in the paper called Matryoshka Representation Learning, MRL.
MRL.
I'm going to struggle to pronounce that for the next hour, I can tell.
Just call it the Russian doll trick. It's easier.
Okay, the Russian doll trick. How does a set of nested dolls help a database search?
Okay, so think about how you search for a book in a huge library. You don't start by reading every single title on every single shelf. That would take a lifetime.
No, of course not. I go to the right section, science fiction, then the right aisle for the author's last name.
Exactly. That's the big outer doll to course general search. Is this relevant? No. Is this relevant? Yes. You narrow it down to one shelf.
Then I look for the author.
That's the next doll inside.
Sure.
The title. So usually in AI, a memory vector is a fixed size, say, 2,560 dimensions. It's a big, heavy mathematical object to move around and compare. MRL allows the AI to use a tiny, low-resolution version of that memory, say just the first 256 dimensions, to do a super fast scan of the entire database.
So it can discard 99% of the wrong answers almost instantly?
In milliseconds. It's incredibly fast. And only when it has the top 10 or so candidates does it open the full doll. It uses the full resolution 2560 dimension vector to find the perfect match.
So you get the speed of a small search with the accuracy of a big one.
Precisely. You get high speed without losing the rich semantic meaning. And on top of that, it's instruction aware.
What does that mean for retrieval?
It means you can actually tell the embedding model what you are looking for. You prepend an instruction to your query. You can say, find the relevant KDE configuration file for this error message. It aligns the search intent.
So it's not just matching keywords, it's matching the user's goal.
Yes, and that improves accuracy by a reported 1 to 5% on technical queries, which is a significant margin.
So we have the model, we have the memory. Now let's talk about actually building QIAcord, the implementation strategy, because Qwen 3.5 has these special thinking variants, right?
It does. They're designed for complex reasoning.
Yeah.
The model uses XML-like tags, think.think, to basically talk to itself before it answers you. It lays out a chain of thought.
Which is great for getting the right answer, but...
But Discord users don't want to see a wall of text where the bot is debating itself. Maybe it's the kernel. No, wait, I should check the driver. Wait, user mentioned logs. Let me look at those.
I wonder if I should suggest using sudo. Am I allowed to suggest sudo as a support bot?
Exactly. It's all clutter. It pushes the actual useful answer off the screen. So the solution detailed in the project's KaiIntelligence.p module, the brain module, is what they call a soft switch.
A soft switch? How does that work?
It's clever. You use regex regular expressions to parse the model's full output. You find and hide the think block from the user. You only show them the clean, final response.
But you don't just throw the thinking away.
No, and this is key. You log the thought process on the server side.
For debugging. So if the bot gives a weird answer, you can look at the logs and see why it thought that.
Right. You can see its reasoning. Oh, it got confused and hallucinated that the user was on Ubuntu instead of Arch. That's why it gave the wrong package name. And you can use dynamic prompting with this.
Explain that.
Well, if the user just asks, hello, you don't need a deep philosophical breakdown of the concept of greeting. It's a waste of compute.
Right.
So you toggle the temperature up to 0.7 for creativity, and you tell the model thinking is O off F. Just give a simple reply.
Simple.
But if the user posts, my Arch Linux kernel panic is giving me this hex code, you toggle thinking on N, drop the temperature to 0.6 for more deterministic output, and you let it chew on the problem. You allocate the heavy compute power only when it's actually needed.
That's very smart. You don't burn calories on hello.
Exactly. And one final implementation detail. Because the new Qwen embeddings are so much smarter and denser, you have to harden your knowledge boundaries. The similarity scores for retrieved documents will cluster much tighter. You need to go back and retune your thresholds in the kaireg.py file so you can properly distinguish relevant from highly relevant.
Now, one thing I found really interesting in the project notes is that they aren't throwing everything away. They are keeping a tiny little Llama 2.2b model in the stack.
The hybrid stack. Yes. This is what good engineering looks like. We engineers love to just throw out the old code and replace it with the new hotness, but Llama 2.2b is tiny. It's a 2 billion parameter model. It runs on the CPU.
So why keep it around? What's its job?
Its job is to be the traffic cop. Intent classification. When a message comes in from Discord, you need a quick, cheap way to know what it is. Is this a technical question? Is this a greeting? Is this spam? You don't need a 9 billion parameter, visually aware expert model to decide that.
You use the cheap, fast, lightweight model for the easy, repetitive stuff.
Exactly. It does its one little job on the CPU, and it doesn't steal a single megabyte of precious VRAM from the main Qwen brain. It's using the right tool for the right job.
I love that. It's pragmatic. So we've covered the architecture, the benchmarks, the hardware, the implementation. As we wrap up, I want to zoom out. How was this thing trained? Because you mentioned million agent training earlier.
This is, I think, the secret sauce. Qwen 3.5 wasn't just fed a huge dump of text from the internet. It wasn't just fed Wikipedia and books. It was trained via reinforcement learning, or RL, in what Alibaba calls million agent environments.
Okay, what does that look like in practice? What is a million agent environment?
It means the model was placed in millions of tiny simulations. It had to navigate websites to find information. It had to write code to solve problems. Crucially, it had to recover from its own errors. and he was rewarded for successful outcomes.
So it learned trajectories, not just text patterns.
That is the crucial distinction. A simple pattern matcher just predicts the next most likely word. A trajectory learner understands the multi-step path to a solution. It knows that if step A fails, it should try step B as a fallback. It has a kind of digital grit.
So let's bring it all home. Give us the verdict, the skeptical engineer's final verdict on this migration.
The verdict is that this is not about chasing the shiny new toy. This is about solving real fundamental engineering problems. It is about solving the 200-second bug. It is about solving context rot. And it's solving these problems at the hardware and math level, not with software patches.
It's changing the physics of the model itself.
It is. And the result is that it allows a consumer GPU, a card you can buy at a generic electronics store for a few $100s, to perform tasks that, just 2 years ago, were absolutely restricted to multi-GPU enterprise clusters costing tens of thousands of dollars.
That is the big takeaway for me. We have moved from the era of the simple chatbot to the era of the autonomous agent. Kayacord isn't just a search engine wrapper anymore. With this upgrade, it's a proactive technical partner.
It's a colleague, a very, very fast colleague.
It's a colleague. And here is a provocative thought to leave you with. If a 12-gigabyte consumer card can now run an autonomous, visually aware, expert-level agent, what happens when these local clusters start talking to each other?
Peer-to-peer, without a central server.
Exactly. What happens when your Kayacord talks to my local agent directly to solve a problem that neither could solve alone? The definition of edge computing just got a lot more interesting.
The mesh network of agents.
Yeah.
That is absolutely the next frontier.
And we will be there to cover it. Thanks for listening to The Deep Dive. We'll see you next time.
See you then.